My name is Krishna Anand and this is my presentation for Assessment 2 of CSC2230 Big Data Management and Analytics. In Assessment 1, we analyzed the 2017 Instacart Dataset, which consisted of 3.4 million orders from more than 206,000 users. This was done using a relational SQL database. Whilst these are great for data integrity, it forces the system to perform computationally heavy multi-table joins for a simple action, just like viewing a customer's receipt. To overcome these limitations and directly address the scalability requirements and design specifications which meet the needs set out by management, I redesigned the architecture into an order-centric NoSQL document model. By embedding the line items directly into the orders collection as a nested array, the system can now retrieve an entire transaction in a single atomic read operation. To build this architecture, I developed an extract, transform, and load pipeline using Python and Pandas to reshape 33 million flight relational records into nested JSON arrays, which were then safely batch inserted into a local MongoDB instance in chunks of 50,000 documents. While transactional items were embedded for rapid retrieval, I deliberately utilized shallow referencing from the product collection, a decision made to mitigate update anomalies and preventing exponential data bloat, which creates a balance so that if a supplier or a manufacturer updates a product's details such as its name, it does not require millions of historical document modifications, and that it would not be costly in terms of storage due to many redundant data entries that would occur if all the information was embedded into a single document for every order. To demonstrate this NoSQL model in action, we will look at Query 1, which identifies the most frequently ordered products. As our products are embedded in an array, our pipeline first deploys the unwind operator to deconstruct the array into individual documents. We then aggregate by product ID using group to aggregate the totals and execute a lookup join to cross-reference our separate products collection for the human-readable item names. As seen in the output, fresh produce like bananas, avocados, and berries dominated the platform, with our top position being bananas at 491,291 total orders. An issue with this application, however, was that because MongoDB processes aggregation pipelines on a single thread, attempting to run this across 33 million rows caused a significant hardware bottleneck, with the query requiring 25 to 30 minutes to complete. To solve this single-threaded bottleneck and highlight just how different these platforms are, we migrated this same analytical workload to PySpark. PySpark introduces a functional distributed mindset, which requires a completely different style of thinking. Instead of executing sequential database lookups, PySpark leverages lazy evaluation and distributes tabular data frames across all available CPU cores in active memory. By chaining .group by .ag and .join, Spark's Catalyst Optimizer constructs a highly efficient physical execution plan, and what took half an hour in MongoDB executed in under 5 seconds in PySpark. Crucially, as demonstrated on screen, bananas once again dominated with 491,291 total orders. When executing these queries across all 4 iterations, our relational SQL baseline, our optimized NoSQL, our fully denormalized proof of concept, and our PySpark iteration, it yielded 100% identical numerical results. This absolute parity serves as a rigorous data audit and proves that our ETL pipeline and transformations maintain flawless data integrity and consistency. Critically evaluating these systems demonstrates that no single architecture fits every workload, which necessitates a hybrid strategy. Relational SQL remains mandatory for financial ledgers, user credentials, and human resource management applications due to its strength and strict asset compliance, and normalized tables which make it essential to prevent data duplication. Conversely, document-based NoSQL MongoDB architecture is essential and vital for the live storefront, offering the schemaless agility and rapid read speeds that are required for an active cart and a frictionless e-commerce checkout experience. However, this struggles with large-scale analytics due to its single-threaded bottlenecks. Whilst I tested a fully denormalized proof-of-concept model embedding all the product data and strings into the orders, thus dropping the query times down to 30 seconds, it was ultimately discarded due to exponential data bloat and high cloud storage costs, which would make this usage impractical in the real world. Thus, ultimately, PySpark is strictly mandatory for the analytical layer, allowing data scientists to perform large-scale online analytical processing without burdening the transactional database, helping to strike a balance between operational costs, the time to insights, and full analytical functionality. Structurally, shifting away from relational databases and towards a hybrid paradigm provides four distinct operational advantages. Firstly, by embedding line items, we convert expensive multi-table joins into instantaneous key-value lookups. Secondly, self-contained documents allow the transactional database to be horizontally partitioned across multiple commodity servers as user volume and the number of orders expand. Thirdly, the polymorphic schema flexibility allows developers to dynamically introduce or alter new attributes like promotional codes, item names, and delivery tags without risking system downtime through rigid alter table migrations. And finally, integrating PySpark introduces distributed in-memory processing, which turns hours of analytical workloads into mere seconds. Finally, transitioning to this highly capable architecture introduces unique ethical, governance, and security challenges which differ from those of a relational SQL database. Regarding behavioral data protection, because NoSQL consolidates an entire completed transaction into a single document, a single breach exposes a comprehensive customer profile. When this is paired with PySpark's high-speed analytics, algorithms can easily infer sensitive, unstated personal attributes like dietary restrictions, medical conditions, and religious affiliations. The business holds an ethical duty to ensure that this behavioral data is used strictly for logistics or demand forecasting rather than for predatory profiling and discriminatory pricing. Structurally, because NoSQL is schemaless, data governance teams must enforce application-level schema validation during the ingestion stage and layer, automatically rejecting any document attempting to write unapproved, sensitive, or financial personally identifiable information, like credit card numbers and raw addresses, to transactional collections. Lastly, distributed clusters also present unique attack opportunities, and when shuffling 33 million records across memory partitions within PySpark, internal node-to-node communication must be secured using TLS 1.3 encryption, alongside the implementation of granular role-based access control in order to ensure that only the necessary personnel and data analysts interact with just the tokenized and pseudonymized datasets. By combining the transactional agility of NoSQL with the distributed analytical processing power of PySpark, we have successfully established a secure, highly scalable, and analytically robust data architecture which resolves the core operational bottlenecks of the relational model and meets the design specifications and requirements of management. Once again, I appreciate your time and thank you for watching.